comparing quadratic, square root, and cube root functions presented in different ways. Lesson 22 of Topic C in Unit 4. Populate the table on the right, x and y, with values from the graph. We have to find points that this graph here, this quadratic function, passed through. Can anybody give me a point in xy form that this graph passes through? It passes through -2. I need a smaller marker. There we go. -2, -1, and that would be right here. Anywhere else it passes through? 0, -3? -3, 0 would be right here. That is -3, 0. What else? -1, 0 is right, and that would be right here. 0, 3 is up here. -4 and 3 would be over here. That is right. Questions about that? What is the vertex for the function on this graph? Which point? -2, -1. That would be here and right there. That is the vertex. What is the y-intercept for the function? To the right 3 and up 0? 0, 3. 0, 3 is there, and that is the y-intercept. What are the x-intercepts for the function? -1, what? The first, just give me one of them in the point form. -1, 0 is an x-intercept, and what is the other one? -3, 0. Yes. Solve each problem and show or explain how you found your answers. Xavier and Shirlise each threw a baseball straight up into the air. The relationship between the height, which is the distance from the ground in feet, of Shirlise's ball with respect to the time since it was thrown in seconds is given by the following function. And then the graph of the height as a function of time of Xavier's ball is represented below with this graph. So we'll just leave that one on the screen and use it as we need it. Now this is Xavier, and the function was Shirlise. That's why there's an S in it. Her first name starts with an S. Alright, the questions are: Xavier claims that his ball went higher than Shirlise's. Shirlise disagrees. Answer the questions below and support your answers mathematically by comparing the features found in the equation to those in the graph. Okay, we have to figure out who is right, but we can't. It's not a 50-50 guess. If it says you have to support your answers mathematically, then you have to do so. All right. First of all, how can we compare whose ball went higher? What can we use from the graph to see how high Xavier's ball went? Where it hits the top and comes back down. What point is that called? The vertex. Yeah, so the vertex of Xavier's throw is there. And about how many feet is that above ground? 75. Okay, so we'll come down here and we'll estimate that Xavier's throw went about 75 feet high. But we still have Shirlise to deal with. And Shirlise has this function here. What can we do with this function to figure out how high her throw went? If I'm going to complete the square on this problem to find the maximum point, which is the vertex, then what is my first step? Group those two together. All right, so if I group those two together, then what do I have to do? Yes, we want to take out a negative 16. So negative 16 times the quantity. And when we divide by negative 16 in each of those, we're left with a t squared. And then dividing in there, we're going to have a minus. If you divide 79t by negative 16, it's going to come out to be minus 79 over 16. T. Look what happens when you go back and multiply it out. Negative times negative goes back to positive. If you leave this sign positive here, you're going to come out with the wrong answer. Alright, so we're going to have that, and then still a plus 6 on the outside. What do I have to do next? We have to divide the minus 79 over 16 by 2. So we're left with this, and this, and this is going to stay the same. But we need space in here so we can put in what's going to happen next. Half of 79 over 16. If I want to find half of a fraction, I do what to the denominator? Don't divide the denominator by 2. We don't put it on top. So half of 79 over 16 is going to be 79 over 32. But we have to square that. 79 over 32 is half of 79 over 16. So on your calculator, if we square that, when you square a fraction, do you square the top only, the bottom only, or both? Both. So we're going to have 79 squared, which is going to be 6241. And then on the bottom we'll have 32 squared, which is 1024. Now, have I added 6241 over 1024, or have I added something different? Yeah, whatever is there in the black, I have to multiply it by negative 16. If I multiply by negative 16, I'm just multiplying negative 16 by 6241 and then putting it over 1024. Negative 16 times 6241 comes out to be 99,856. Now remember, we're doing minus. It's a negative 16 times that positive fraction. That comes out to be minus. So what we're doing on the outside must be plus. So we would end up with 99,856, and then putting that over 1024. Alright, if we put this in the completed square form, we end up with negative 16 times the quantity t minus, and then remember we need half of the 79 over 16, which is, and I'll draw a line here because it looks like I'm setting all that equal to 79 over 32, but this was half. Let's put that in a form that we can use. 79 divided by 32 really comes out to be 2.47. So let's just put that in there. Close quantity and square. And now we have 6 plus that strange fraction out there. Let's find out what that strange looking fraction is in terms of a decimal, and then add 6 to it. 99,856 divided by 1024 is 97.5 and some change. And if I add 6 to that, then I come out with plus 103.52. Now, from Shirley's function here, can we figure out what the maximum point is?
2.47.
That's right. That is the vertex, and since it opens down because of that negative, it's a maximum point. Now can we figure out what each of these numbers mean? What is this number? What does that represent? How far to the right, and what is that? The function was in terms of t. What does t represent? Time. All right, so we end up with time. And then what does this represent? It is the height. Okay, so let's go back over here and take a look at this one. He went up to about 75 feet. How far did she go up? About 103.5 feet. Yeah, so which one threw it higher? Shirley's, right. So who is right? And we can say Shirley's. I'll probably butcher this name. I mean, this might be close. Yeah, it's written right here, so I did get it right. And we did that, and we proved it mathematically over here. On a test, you can't just pick a name and leave out all the work. If you do, you're missing over 75% of the credit. The next question is, for how long was each baseball airborne? We'll start with Xavier. How long was his baseball airborne? About 2 seconds, yes. And we can come up with that from drawing a line down through where we think the vertex is at, down to a 2. So we come up with Xavier at about 2 seconds. And we already looked at Shirley's. We determined that hers was 2.47 seconds. And we get that from this over here, from the vertex. Construct a graph of Shirley's throw as a function of time, t, on the same set of axes as the graph of Xavier's, and use the graph to support your answers to parts A and B. You have to use what we found in Shirley's function and in completing the square. Her vertex was 2.47. And then it went up, what was it, 103.52? There we go. So if we go over 2.47 and then up 103.52, look how strange the y-axis is on this. It's skipping up by 12.5, it looks like. So we need 103.52. In here, halfway between 100 and 112.5. would be 6.25, so that's 106.25. We need about 103, so it's going to be right here. And she went 2.47 seconds. So we're going to go halfway between 2 and 3 and just put a dot there. Alright, we can come down and draw the graph. We would be approximating this, drawing it freehand. We could find the x-intercepts, but I don't think there's a need to do that on this. Mine is a little bit wide. That's a horrible looking graph, but you get the idea. And notice how the graph illustrates that she went much higher than Xavier. At an amusement park, there is a ride called the Center. The ride is a cylindrical room that spins as the riders stand along the wall. Cylindrical means this, kind of like a can. As the ride reaches maximum speed, riders are pinned against the wall and are unable to move. The model that represents the speed necessary to hold the riders against the wall is given by the function S of r equals 5.05 times the square root of r, where S equals required speed of the ride in meters per second, and r equals the radius in meters of the ride. So radius in terms of r, if you're in this ride, we have 4 for the radius on that. In a competing ride called the spinner, a car spins around a center post. The measurements in the table below show the relationship between the radius r of the spin in meters and the speed of the car in meters per second. So we have this function for the ride called the center, and then there's one called the spinner, and it's represented by that table of values there. Due to limited space at the carnival, the maximum spin radius of rides is 4 meters. Assume that the spin radius of both rides is exactly 4 meters. That helps us tremendously. Both are going to be 4 meters. If riders prefer a faster spinning experience, which ride should they choose? And show how you arrived at your answer. The spinner is which one? The table or the equation or the function? The table. How fast does it go with a 4 meter radius? 15.588. And we came up with that by looking at the table. So down here, let's take note of this. The spinner with a radius of 4 will have a speed of the following: 15.588 meters per second. Is that all we need to solve the problem? Yes or no? No. Well, that takes care of the spinner. Where is the center at? It's the equation up here. It is the function. How can I figure out how fast in meters per second the center ride goes with a radius of 4 meters?
5.05 times the square root of 4.
That's right. Insert the radius of 4 into that function. So we'll come back down here and we will list the center ride. It has a function of, and the exact notation is S of R. So we will put S of R equals 5.05 times the square root of R. We want to test it out for a radius of 4. So S of 4 equals 5.05 times the square root of 4, which comes out to be 2. So 5.05 times 2 is going to give me a speed of what? 10.1 meters per second. Which one has the faster ride? The spinner. Yes, the spinner has the faster ride. Compare those two and come to your conclusion. The growth of a Great Dane puppy. The growth of a Great Dane puppy can be represented by the graph below, where Y represents the shoulder height in inches and X represents the puppy's age in months. So we have inches and then months. Inches is on the y-axis, months is on the x-axis. And that is for a Great Dane. So we'll go ahead and write that in here so we don't have to look for it in the text again. The growth of a lion cub can be modeled by the function represented in the table below. That one has months and that one has inches. It even tells you that this is X and this is Y, just as in the graph above. Which animal has the greater shoulder height at birth? What is the shoulder height of the Great Dane at birth according to this graph? 12. All right, let's look here. This is 8, so if we go 10, 12, 14, yeah, it looks like it's at 12. So we'll go with the Great Dane at 12. All right, so down here, the lion cub at birth is how long in inches? Or no, how tall in inches? 8 inches. So LC, 8. Which has the greater shoulder height? The Great Dane, yes. Very simple problem to solve. You just know how to read a table and a graph. Which animal will have the greater shoulder height at 3 years of age? The age each animal is considered full grown. Three years of age. How many months is 3 years? 36. All right. So this over here is 32, 34, 36, 38. Here is 36. What is that shoulder height approximately? It looks like it's about 24 and a half. Yeah, I'll go with 24 and a half for the Great Dane. All right, what about the lion cub at 36 months? Is it on the table? No. Does it need to be on the table? How can we figure out what the lion cub is going to be? What was the growth, approximate growth from 16 to 24? 16 to 24, it's about 2. And then from 24 to 32? About 1.4. The growth is getting smaller. So going up to 36, look at the difference between here. This is 8 months difference here. And it's less than 2 inches in growth. Now according to this table, this next one is going to go up to 40. So at 40, we could expect it to be a less than another 2 inches of growth. All right, up here, we see this. There it is at 32, or not 32, but 36 right there for the Great Dane. It's at 24, and we know we're going up 18, 20, 22, so this would be 26. And look at how this thing is curving. Probably not going to make it to that, out to there, and that would represent 26. But this is already at 36. It can't go any further in this comparison. Will the lion cub still have more room to grow? Yes, because right here it's already at 23.874. It still has 4 more months to grow. The Great Dane is finished growing at here. 24.5. So with another 4 months worth of growth, certainly this should pass the 24.5. So the lion cub would have the greater height.